you're like, that too should go to everybody. And I'm like, no. Why are you taking it to everybody? There's no addition. There's no subtraction. Come on, a couple of you would think this. There is no distribution because there is no addition or subtraction. If I have a constant in front, it's just good old-fashioned times. Yeah, he's in parentheses, but that doesn't make anything any more important than the other. It's times, 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 times. That's it. So 2 times 3 is 6. Dun, 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 dun. There is no distribution. Distribution only happens over addition and subtraction. Coming back to the vector thing, this is just a warning that if you see something like a constant in front, don't you dare take it to the u and the v and then do a dot product. You have to do the dot product first and then multiply, or just take the constant to one of them. Now here's one other way that maybe more of you would make a mistake. What if we were to multiply something like we can't solve it because it's not equal to 0. So we can't just set each equal to 0. Bummer. We have to multiply it out, get it all to one side, and then try to factor or complete the square, quadratic formula, or something. How do I multiply the 2? You distribute it to, long story short, one of them and not the other. It's good old-fashioned multiplication. PEMDAS says parentheses, but I can't. They're not like terms. Multiplication. Okay, I could FOIL and then bring in the 2. That's legal. Or I could just bring in the 2 and then FOIL. Or I could bring in the 2 and then FOIL. But the long story short is I cannot, I should not, I would be totally wrong if I brought in the 2 to 1 and the other. There is no addition, there is no subtraction, there is no need to distribute further. This is a more practical application of you should only distribute it once. Or some of you are like, I would just get rid of it and not even worry about it. Okay, that's another way too. But that's what this is saying. When you have a C, a constant times a vector, Nathan, I'm coming to you. That multiplication, that C is only allowed to come into one or the other or dot product and then bring it in, not to both. Okay, what's that?
Couldn't you distribute the last one? Couldn't you distribute the 2 and then factor the 2x?
But there was a plus or there was a minus, so I can't. There wasn't an x in both terms. You're seeing that there would have been a 2x in both. I see it. Now it's on. You should. Just kidding. Don't do that. I don't remember exactly what was there. Was it something like this? You're thinking like, hey, this becomes, and I get it. The problem is, I can't just factor out from an addition or a subtraction because they're grouped. See it? Yeah, if it was a times, I could pull out a 2x because it's plus and minus. And then,
That's good.
Yeah.
Did you FOIL before bringing in the 2 or after?
To be honest, I'm a lazy person. I would FOIL first because I want them to be as small as possible and then worry about it. To be doubly honest, I might have just moved the 2 and said forget it. 4 divided by 2. Technically, Aiden, all of them are legal as long as they're so. But if you're not sure, do order of operations and do whatever else is there and then bring it. That's the safest way. So along those lines, hold on. I need you guys to see a dot product. Okay? So dot product. Oh, there are I's and J's. It's all right. We already dealt with that yesterday and the day before, right? If we don't like I's and J's, what can we always do? Good terms. Components, right? So the first one, you could just rewrite it as
4 negative 2.
Got it. Second one, you could just rewrite as
1 negative 1.
Now my question to you is just to pause and to ponder the formula that you've already written for how to multiply 2 vectors. Do you understand what it's telling you to do? Who is U1? Who is U2? Who is V1? Who is V2? In some ways it's such a basic formula, and yet if you don't understand what it's saying, how do I do U dot V? Wherever your brain went, complete confusion or complete understanding that might be wrong or complete understanding you might be right. Can you check it now with me? All you gotta do is say who's the x times who's the x plus who's the y times who's the y. Multiply the horizontal components, multiply the vertical components. The final answer is not a vector. Not a vector. Final answer is not a vector. Add 2 vectors, get a new vector. Subtract 2 vectors, get a new vector. Multiply 2 vectors, get a number?
Why do they always use U and V and I and J? Why not other letters?
I think U and V. They like using letters at the beginning of the alphabet for like the pieces like A, B, C. Like A and B are the different components and whatnot. They're keeping away from X and Y for obvious reasons. Once you get into the vowels, it's kind of awkward because like E is actually representative of some things. They don't like to get in there. Middle of the alphabet, a lot of people aren't used to what letters come next or after each other. They don't use T because T is time. So it's kind of like T, U, V. Oh, I think it's literally just like A, B, C, T, U, V, I. It's just easily memorized or remembered. But even in your calculator, if you were to go to something called in the modes, sequence mode. We've been in function mode. Before the end of the year, we'll be in par. Oh, were we already in par mode? No, we weren't. Before the end of the year, we'll be in par mode and pol mode. It's func, par, pol, POL, and then SEQ. If you go to Y equals in the SEQ mode, they use U and V also. Or if you look at second 7 or second 8, I think there's a little lowercase u, lowercase v at. Okay, that's a great question. I don't have a great answer besides I just think, oh, U, V, W. And then it's X and Y, which is already being used, and Z is by himself. There'd be no like succession of multiple. So if we have something down below, do you guys see how the formula works though?
Yes.
Horizontal plus vertical equals a number. So down below, when we have like a succession of v dot u with w dot v with a minus, the nice thing is if you do v dot u or u dot v, it's the same thing. So what we just saw on the page before is you can totally just do these in any order. But they are both numbers, and they're both going to end in a subtraction that results in the final number. But we're just practicing the dot product formula. So how do we do v dot u? Technically, if we were going in the order that it was written, what would v dot u be? Okay, x times x. Good. Negative 4 times 3. See it? And now it's time for
2 times 3.
y times y. 2 times 3. Which I know some of you can do that mental math. I'm just showing where it comes from. Or else it's going to be, let's see, a random number. Minus, time for this guy. Okay, w dot v. Okay, so the x to the w times the x. Got it. It's really hard to show you guys, actually, to be honest. I don't think I have the correct comprehension of it to even try to show you what a dot product means in terms of a vector diagram. It really doesn't. It really doesn't have a meaning in terms of the vector diagram, like, oh, it's a force and a force and a. But a dot product is something with vectors that is used, able to be applied, fundamental to a lot of different relationships between vectors that we're going to see. So section 6.4 is basically, like this dot product thing is important in physics. Like, you're going to see it, and it's going to need to basically be something that's just super secondhand, super off the tip of your tongue. Super basic, basically. So we're just trying to be able to get the math down, get the formula down, and be like, oh, that's how you do it? Easy, it's not that bad. So I just have negative 12 plus 6, which is negative 6. And then I have negative 12 minus 2, which is negative 14. My final dot product from this little equation, or I should say my final constant, would be 8. We're just trying to get down to where the math of the formula, or plugging into the formula, you guys pretty much understand. And then we're going to use it in a few ways. But in physics, once again, this dot product guy, man, he's important all over the place. He's applied all over the place. So this section, the point is not to master these applications. It's literally this dot product guy is important. And let's just play with him a couple ways and see how to solve with him. So far, we just said, what is he? How do you use him? Now let's figure out how to use them. Not an exhaustive list by any means, just a few. Just a few different applications. So one application. And the nice thing is he saves us some geometric work. He saves us some log cosines, log sines. Which once again sounds like a party, but if we could avoid it, let's. Let me make these arrows really dark for you because what we haven't seen thus far is what vector subtraction looks like. Well, okay, we did. But we just said vector subtraction was vector addition of the opposite. But another way of seeing vector addition of the opposite is what you see right here, which is vector subtraction. You guys go ahead and get down this formula for angle between. I'm going to try to show you why subtraction says let's connect them tail to tail. That's kind of a weird concept. Once again, it's not the point of the section. It's not like the biggest thing you need to master. Just, it's interesting. There we go. You guys want to see why that's vector subtraction? Took me a second, sorry. V minus U, V stays the same. U with a negative flips the direction of U, so instead of going up and to the left, it's going down and to the right. But then it's already head to tail, so all I have to do is connect. Anyway, that's a reason why vector subtraction is just connecting. Wow, there's a lot. Oh my goodness, someone help the people out. V minus U is just connecting head to head, and it makes it a lot easier than actually having to show why it's head to head. But if vector subtraction is head to head, there might be times where it might be helpful to find the angle between. The struggle is to find that angle between. We would either need side, 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 and law of cosines. But we were talking about how you can't find this unless you use a law of cosines knowing side angle side, so that's not going to help. We could do parallel lines, and we could have all sorts of fun. That might be one way of saying it. All sorts of fun, where we make like parallel lines, and then we think about like our transversals, and we think about the angles that we. Wait a minute, this will be so awkward because we're going to maybe know this angle outside the triangle, this angle outside the triangle. Like I don't even know. I guess we could subtract from 180. Anyway, there could be another way. Especially if this is out somewhere away from the origin and tilted, man, that would be a lot of hard work because this wouldn't even be a horizontal anymore. A better way is just using the dot product and this formula that the dot product is used in. So if I'm trying to find the angle between two vectors, if I can have their components, all I have to do is throw into this formula. But guys, this formula, if you were thrown this on a physics worksheet, if you didn't know what magnitude was, if you didn't know what components were, if you didn't know what dot products were, like, how do you even do the formula, right? But now that we've learned all this stuff, let's just practice it in context of, oh, you can find an angle this way? Cool. That helps me avoid all the other law of cosine, law of sine stuff, and geometry, parallel lines, alternate interior, blah, blah, blah. So, cosine of theta is equal to. Let's practice. Dot product of this guy. Wouldn't that be 3 times 4 plus 2 times 0? We're going to be practicing dot product. Yep, just going to be 12. All over. Magnitude of. Isn't that square root of the Pythagorean theorem, dude? 3 squared plus 2 squared. Bless you. Times magnitude of. Look at me. I'm just sneaky and making you practice all the stuff you should already know. Bless you. We end up with 12 all over square root of 9 and 4 is 13 times square root of 16, which is just 4. Okay, that's 1, that's 3. So my angle is 3 over rad 13, right? That's a weird angle. formula, if you were in physics, would you make this mistake or would you know to keep going? Aiden, now's the right time for your inverse trig. Who's on the other side? I don't have my angle yet. I only have a cosine. Yes, how did I do it?
I meant the square root and the bottom.
Rationalize.
Yeah, I could. I'm gonna go to my calculator anyway. But yeah, you're right. I could make it 3 with 13 over 13 and have to type in more. How do I get to theta? Our cosine or cosine inverse. Nathan, be helpful. Our cosine. Now's the proper time. I need the theta. I don't have the theta. The whole point was the theta. So maybe some of you might want to write in like law of cosines in order to solve for actual theta, the point of the formula. You have to take cosine inverse of both sides. Nice thing is it's not sine inverse, which is that weird ambiguous SSA guy. Cosine inverse gets you straight to the only possible angle that could be in a triangle, which is awesome. You end up with theta is equal to, I don't know, something kind of nice. Favorite degree mode? Anybody back him up real quick? It's always dangerous to take the word of one person and say that. Okay. What does this help you avoid? Drawing any pictures, doing any geometry, remembering anything from parallel lines, and doing any law of cosines, law of sines. Sweet. 2 magnitudes, 1 dot product, and 1 cosine inverse. That's nice. What about this one? Orthogonal, there's a term? There's vocab? Yes, we've been saying vocab nonstop for the last week. Orthogonal. Orthodontist. Who's been to one? Me, majority of my teenage years. Anyway, orthogonist. Orthogonal. What do orthodontists do? What's ortho? Orthopedic surgeon. Ortho. What's ortho? Ortho. What do they do to your teeth? Straight. Oh.
Clean.
Well,
They do.
Yes, they do.
they get on you if they're not clean, though.
That's dentist.
They
Ah,
do
the
it
orthodontist
before.
used to get mad at me
Destroy
too.
your teenage lives.
Before they do surgery, they clean them a little bit.
Yeah, that makes sense.
Sorry.
Yeah.
Orthodontists, are they the actual surgeons? Mine wasn't. Mine was a separate surgeon. What are they called though? Teeth? What's a snazzy name for someone who operates on teeth? Like surgeries?
Orthopedic surgeon.
No, not orthopedic. Orthodontist? Maybe.
Oral.
I went to UCLA, but I forget who the guy looks like.
Oh.
Oh, yeah, oral surgery. Thank you. Oral surgery. Anyway, orthogonal. Orthogonal. Ortho, straighten, straight. 2 vectors coming together at, okay, it's awkward because all vectors are straight technically, they're all lines. You can think a crooked line is like a diagonal line. Anyway, I don't know. However you want to remember it, they're perpendicular. There are 2 snazzy names in physics for perpendicular. One is orthogonal, and the other one, I'm just going to show it to you now, is normal. What? That's okay. That's fine. I don't know.
You get a word like orthogonal.
I know, and then normal. I know, right? Normal. But I've kind of been saying this because I mentioned the normal force when I meant the perpendicular force. Maybe some of you caught it, maybe some of you didn't. But normal is another way of saying perpendicular. So if you ever see normal in a math context, it's not talking about like what's not strange. It's talking about literally perpendicular. But orthogonal, normal, perpendicular. Perpendicular means coming together at a right angle. There we go. Whew. All right, we're doing good. So if we have, oh dear. If we have a vector u and if we have a vector v, you guys are so much more fun when there's very many people here. Just kidding, there's so many people here. We got like 5 are gone and you're all like talking.
There is more than 5.
There's like 6.
There's at least
7, we'll do the number of completion. So we have u and we have v. Wait a minute. If they're perpendicular, doesn't that mean their angle is 90? Didn't we just have a formula that talked about the angle between them? And wasn't the angle between them cosine of theta is u dot v all over magnitude of u with magnitude of v? What would happen if that was a 90? Cosine of 90. Wait, we know that. What is cosine of 90? 0. So that's 0. Wait a minute. So that's 0. Multiply the magnitudes up. They don't matter. What matters is the dot product. All I need to know is the dot product. I don't even have to plug into this formula and see if it's 90. I just get to say if the dot product is 0, they're perpendicular. If it's 90, I'm done. Because vector multiplication works differently than polynomial function number multiplication, and so it's just a way of saying it is vector multiplication, but they're making it separate, distinct. So they say dot because of dot. Okay. Don't read the last page of that until you get to the last. I was seeing how many pages were left when I was in high school, and then I accidentally didn't realize the story literally ended at the very last page instead of like it being an ad or something, and I read the last sentence and it ruined the whole thing. You're welcome. Will you abstain from the temptation?
No.
It's summed up in the last sentence. Anyway, coming back. What is this guy? Because Nikki is not exactly totally focused on that. Isn't it awful? Yeah. Yeah, right? How many?
So yeah.
Well, no one else do it because it kind of ruins it. All right, so what are the components for you if it's just I? 1 and 0 because there's no j. How about this guy? -2 and 2. And I'm trying to see if they're orthogonal. It's as easy as a dot product, and I need to interpret what the dot product means. This is easy as a dot product. What's 1 times -2 plus 0 times 2? Not 0. So what is it not? It's not orthogonal. Now, could I find the angle? Sure, there's a formula for that. We just practiced it. But are they asking for the angle? Nope, they just want to know whether or not it's perpendicular. Why? Well, if two forces are perpendicular, the projection of one force onto the other force is 0. Projection? What is she talking about? Movie screens? Projection. You all got excited? Sorry, not movie screen. Kind of. Mostly not. Vector components. Wait a minute, I think a million things have been called vector components in this section. Let's call this projection, just because that's what we're actually talking about. Projection. If you guys notice, neither of these are at 90 degrees. One is at an obtuse angle, the other one's at an acute angle, two vectors working together, acting on a common object. I should put it that way. What am I saying? It's okay, you're here and we'll just be thankful. So, here we go. Obtuse angle, just stay alive. Acute angle. It's okay. Senior days, I know. Abby's trying to be alive today too.
I didn't play yesterday.
Seriously.
No, not 1 minute.
You did a J unit.
Oh, I forgot that. That's true. Coming back. Obtuse angle, acute angle. Long story short, projection is a really complicated idea.
Stop crying.
We'll say it was done out of blood. Projection is a really complicated idea. Nice news, it's not on the test.
Yay.
Weird news, then why not talk about it? Reason is because it leads into the basis of the idea. No, not calculus, actually. No, there is vector calculus, but that's not at all a high school level, and you would see that in like a calculus-based physics course. Let's just go to all the different. Come back. So, the reason we're talking about projection is because projection leads into the idea of work, and work is something that we do need for the test. So, projection, I think you have like maybe 1 or 2 homework problems. It's not a huge deal. But projection is complicated. Now, hold on. I need you guys to write right down here that this thing is a very hard projection problem. Nathan, hi.
Sorry.
This is a very hard projection problem. This is harder than anything that you would see on the test. In the sense of this would be Someone, oh, I don't even know how this would be. Hold on. I'm thinking something is on a slope and is naturally sliding down the slope, but then you're trying to pull it this way. That's a really awkward, but that kind of works. Something, you'd be a really tall person, because it would be, goatee. That's a really weird example. I would much rather have it be something that's a little bit more like this, and then maybe like this. In that you're walking downhill and you're trying to drag something with you, but it's too heavy or it's too awkward for you to be dragging it perfectly along the hill, like parallel to the hill, so you have something slung over to your shoulder and you're pulling it down. Awkward. Especially since we didn't have homework ready today. So we have something slung over our shoulder and we're trying to drag it down. That's kind of what's going on whenever you have a slanted picture like this. Now, if it's on a horizontal and we're trying to, if we're trying to move it horizontally, all the math gets way easier. So we're building up to the horizontal one, starting with the diagonal one. And this whole projection thing is the pretend something is slung, like a rope is slung over your shoulder and you're pulling the stool. Now, if everyone was here, I'd probably actually show it, but since it's only you guys and you're all crazy anyway, just kidding, at least today you are. Just imagine, I went back, I got my rope, I tied it around, I slung it over my shoulder, I started dragging the stool. Okay? Is the stool, literally, well, first of all, me with the rope slung over my shoulder, can you guys see the vector of the force or the tension that's at work with my pulling? Do you see it? It's diagonal. But where would the stool be going? Would it be traveling up that vector? No, it's dragging along the ground. If it was starting to climb up that vector, I better drop the rope and run away because that's weird and that's scary, right? I have it, I'm dragging it. What's happening? As a result of my force being exerted, the projected force is dragging the stool horizontally. Oh, projected force. Wait a minute. Okay, so you're acting, you're pulling this way, and yet what's projected, what's happening, what's going on as a result down here is this movement. That's kind of what's going on in projection. There's like some sort of force acting at a certain angle to the actual movement that's occurring. So this one down here, if we were to actually find the projection, we would just need to plug into this formula that, okay, that's weird. Hold on. Whoa. Use your skills with vectors just to tell me what these pieces are. Like, how do we even plug in? What's this?
Dot.
What's this? We have a dot product over the magnitude of this guy. Wait. Only this guy. Not U and V, but V. Okay. All times V. So U dot V, both of them are used up here. Only V is used down here. And it's because this is like me with the rope slung over my shoulder, and this is the stool. U is what's acting on V. So who's the guy who's actually moving? V is. He's the guy that I need to see how U is affecting him or use force. So how do I apply it to this guy? I just plug and chug. But wait a minute, we don't even have components. Oh, come on, be amazing. How do you make components if you know the initial point and the terminal point? How do you make components for, ooh, that's tricky. You guys don't know who's who. This is your U, I apologize, and this is your V. What are components for you using starting at 0, 0 and going to 6, 4? 6, 4, yeah, it's as easy as that. If it starts at the origin, it's easy. How about vector V? 2, negative 3. So how do I plug into the formula? Doing what you guys just told me to. Didn't you just tell me to take a dot product?
2 times 6 plus 3 4.
I'm just doing it in order of UV, but yeah, technically it's commutative.
And then over 2.
Mm-hmm.
And let's write in 2 and 3. And then
Oh, wait a minute. And then this is how U's force exerted at that angle is affecting V. Okay, wait, it's affecting V. I need V's vector to be like, hey, this whole constant needs to multiply by what V is trying to do. So let's see. 12 minus 12 is So what's the overall effect? Nothing. The overall effect is nothing. How is the overall effect nothing? I see it pulling. It's bound to change something. It doesn't change anything. Why? They were orthogonal to begin with. Whenever you have something that's orthogonal, I wouldn't be pulling it to the side. I'd be pulling it right here. But as I pull it right here, I'm not literally trying to lift the stool. I'm trying to drag the stool. How's the dragging going to go if I'm just doing this? Not great. The projection is 0. Now, as soon as as soon as it was an acute angle or an obtuse angle, there would be an effect. There would be a projected force. But otherwise, if I'm trying to drag that stool and I'm lifted straight up, forget that projection. There is nothing. So I guess there is a shortcut. You could always take the dot product first and make sure it's not 90. And if it's not 90, okay, fine. There's a projection on both sides. So, complicated idea in some ways, as far as exactly what's going on and what it means, etc. However, once again, projection isn't on your test. Projection is barely in your homework. And what the whole point of projection is that projected force is important when we get to work. If this stool was 2,000 pounds and I was pulling with all my weight straight up or even to the side, even if there was a projected force, if it didn't budge, if it didn't move, was any work done? According to the definition in physics, no. Work is only done, no matter how hard I'm sweating, no matter how hard I'm going to hurt afterwards. Work is only done if it moves. How do I know that? What's the definition of work? And if the distance is 0, if it never moves, what did you technically never do? You never worked. Awkward. One of those weird ideas in physics where it's like, wait a minute, but work is effort? Or is it result? Weird. Anyway, coming back. Ooh, we could totally apply that to like grades. Anyway, no. We'll stop. But as long as you put in force at an angle, it's not as simple as just, what's the force times what's the distance? Because I'm not literally getting down here with a rope on the ground, pulling exactly along with the motion. No, who's going to do that? I'm going to slip it over my shoulder and be like, whatever, come on, stool, let's go. To that end, I can't just say what force am I exerting times what distance. I have to say, no. What force is being projected times distance. And so tomorrow, we will see how to finish section 6.4 by doing a work problem. Bye, guys. See you later. Adios or quad. If homework is not due until Monday. Tomorrow, we'll see work. Well, finally. People who are gone, you know what to do. Check out the video on the weekend. People who are gone today and tomorrow, better check it. People gone today and I'll see you tomorrow. Well, I'll see you tomorrow.